Hello, so I want to do, again, I want to focus on this problem again. This will be the fourth video since on this problem. The first two, we looked at the forces. The third one, we looked at calculating the electric field and then determining the force. And when I calculated the electric field in the third video, I used a very physical method of determining it. And this time I'm going to use basically method 2 in our notes, which is not as physical as the first method I gave you. And you may wonder, when we look at this triangle in the equilateral configuration, does it have any practical applications? And it turns out that there's a lot of molecules in nature that have this configuration. In fact, the simplest triatomic molecule is called H3+. And it's not really until the last 20 or 30 years that people have really studied this molecule. And it is basically essentially 3 protons at the vertices of the triangle with the electrons floating around inside the triangle. And this is an important molecule. This molecule is actually an important component in interstellar gas clouds. And because it's a proton donor, it's responsible for the buildup of complex organic molecules in the universe. And these complex organic molecules are life-sustaining molecules. And in fact, there are some scientists that say that this is the molecule that built the universe. And of course, there's other molecules with this configuration. So this might look like a simple problem. You might say, okay, what's the application? But the chemists study this, and when they look at the structure of a molecule, they look at the electric forces between the particles in a molecule. Okay? So anyway, let's use method 2 to solve this problem. Now, the thing to remember is when we write the electric field vector, here I'm writing a vector. The Q here has no absolute value sign. The previous video did. And then I have to determine my r hat, which is a vector that points from the source of the field to the point in question. So in my picture here, I'm going to draw the unit vectors for r hat. And I want to determine the field at point P. So the unit vector for this guy goes from the point to the source, from the source to the point. I'll call it R1 hat. And this one goes from the source to the point. This vector does not indicate the direction of the electric field. All it does is indicate the direction of the unit vector r hat. That's it. There's R2 hat. And these are unit vectors. We can easily find their components. X component, Y component. Remember, it's an equilateral triangle, so all the angles are 60 degrees. So this is sine of 60. Cosine of 60. Same thing here. The only thing is that the x component is in the negative x direction. The y component is the positive x direction. And so when I write E1, if I label this particle 1, then it's going to be k times q. And again, I'm suppressing the units because they're in space. And let me put the unit vector r hat, r1 hat, that's this unit vector. We'll do the same thing for E2. And just in case you're curious, I'll put newtons per coulomb at the end for the units. Okay. Here, when I put the charge in, I will put in the actual sign of the charge. And when you distribute the minus sign through into the unit vector for R2, which I'll write here, minus cosine 60 degree I hat plus sine of 60 degree J hat. When I distribute that minus sign through to the unit vector, it'll actually give me the direction of the field. Okay, so E1, if you do this on your calculator, you get the same as the previous video. You will get $36,000 I hat plus 62,350 J hat newtons per coulomb, and then E2, you'll get 71,900 I hat. I'm sorry, minus 71,000 I hat minus 124,600 J hat newtons per coulomb. And then I add them. When I add them, I get 107,900 I hat minus 62,250 J hat newtons per coulomb. Which is the same thing as we got using method 1 that I described in your notes. And of course, we can always ask again, what is the force on a charge that we put at point P? In this particular example, if you put a 7 microcoulomb charge at point P, what is the force on it? Well, the force is Q times V. I will not proceed with the calculation, but it's pretty obvious. You take this vector and multiply by 7 microcoulomb, and you will get the same answer as we got in the first 3 videos. All right, that's it.